Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox. I'm titling this exercise Granular Filter Design for Pier Riprap. So just as it sounds, we're going to be using the Riprap calculator to design a filter, and we're also going to be using the channel calculator. I'm going to leave a link to the lesson on this topic, Riprap filter design, in the description if you wanted a little bit more detail, because I'm just going to jump right into it. Here is the problem statement on the screen. Find a riprap filter design. So it's sort of a open-ended problem statement. Multiple different designs will satisfy. We're also provided some channel data, some pier data, and then some soil data, which is the soil that is associated with the riverbed. So we're going to have the native soil, which we have the data for right here. On top of that will be the riprap, but between the riprap and the soil, we're going to need a layer or perhaps multiple layers of filter. And that's what we're expected to design here, the riprap filter. Okay, so we also have a diagram here of our cross section and our bridge. Needless to say, this is not the scale, but just keep in mind, we are going to be needing all of the dimensions that you're seeing right here. All right, so I'm going to minimize that for now. Let's get started with our channel design. So I'm going to right click, new channel analysis, and then double click to open up the calculator. We're going to use the trapezoidal shape, and the side slope was 2:1, and the base width, okay, it looks like I'm using meters. 1 second, I'm going to click OK. Switch the units over to US customary. I'm going to go ahead and save this. I'm going to call this project 2. Okay, click on save. Okay. Anyway, back to the calculator. The base width, let's see here. I'm going to toggle back to the problem statement a couple times. The base width is 20 feet. The depth is 6 feet right here. The Manning's N is 0.04, and the longitudinal slope is 1%. So I'm actually going to look at this on my other screen here, just so I don't have to keep going back and forth. Okay, so channel width, 20 feet. Longitudinal slope, 0.001 is the same thing as 0.1%. Manning's roughness, 0.04. Now, we don't know the flow rate, but we were given the depth in the diagram, and that was 6 feet. Okay, click on calculate. We have a flow rate of 578 CFS, average velocity of 3 feet per second, and a number of other hydraulic properties are calculated over here to the right. Okay, we can check out the plot if we want. There it is. We're going to have our bridge going across the top and one single pier at the midspan. So we're about to head over to calculate the pier data and the riprap associated with that pier. So I can click OK. We're done with the channel analysis. That's good. Now let's start on a riprap calculator. I'm going to click on calculators and new riprap analysis. Go ahead and double click on that. And for the structure type, I'm going to select pier, which is right here. The channel, we've already created the channel, which is this one here, channel analysis. We have our 578 CFS of flow. The depth is 6 feet. The bottom width is 20 feet, side slope 2:1, and transfer values from channel. Okay, we're looking good already. The velocity input type, I'm going to use average velocity. And then the channel average velocity is 3 feet per second. That is just a calculated value that came in through when we transferred the values from our channel calculator. The velocity adjustment factor, we were given this and we were told to use 1.7. Okay. The note over here to the right says that it ranges from 0.9 to 1.7. 1.7 is if the pier is located in the middle of the main channel, which is what it is. All right, the pier width we were given is 3 feet. And then no information was provided for contraction scour depth or bed form depth. So I'm going to just leave that at 0. And then the specific gravity of the riprap of 2.65. That works. So that is all of our data input. We should have a D50 calculated. It looks like it's 117 millimeters. So that would classify for a class 1 riprap, as we're seeing right here. And the D50, 15, 85, and 100 values of the riprap are all listed out right here. These are the values that the average values associated with the class 1 riprap. So this is the gradation of the riprap. Next, what we're going to do is click on this geotextile/granular filter design button in the top right. This is going to bring up a dialog box that allows us to design the filter that is between the base soil, and our class 1 riprap. So up in this list box right here, we have riprap and soil. It's not letting me select the riprap right now because it's forcing me to define the soil. But once we define the soil, we can click on any of the layers and it'll tell us if that layer is stable based on the layer beneath it. Now the soil is at the bottom layer, so it is by default stable, but I still need to define its properties so the calculator can determine if the layer above it is stable. Because there's a chance, not likely, but we may not need a filter at all. So with the soil layer selected, which it already is, click on this define gradation curve data. And by default, it's giving me 4 different points. But if I had 5 points or 6 points, whatever, go ahead and type that number down here in this number of XY points text box. This is where I'm going to enter the soil data for my D15, D50, 85, and 100, as well as the hydraulic conductivity in units of inches per second. Okay, so grain size is 1, 3, 5, and 7. And then the percent finer is 15, 50, 85, and 100. I'll click OK. We can plot the gradations now. So over on the far left, this brown or tan line is the gradation of the soil. And then this red line here is the gradation of the riprap. So if we need a filter, it's going to be a gradation somewhere between the native riverbed soil and the riprap. So I'll close that for now. The other thing we need to provide is the hydraulic conductivity, 0.02 inches per second, and then tab off. Okay, we have some results here for the D50, of course, that's pretty trivial, is 3 millimeters. Now, if we click on the riprap layer up here, it now tells us that this filter is not suitable. Well, there really is no filter, so it's just looking at the next layer down, which is assigned to the soil. Okay, so no surprise there. Let's go ahead and add a granular filter, which is going to have a gradation, again, that's somewhere between the riverbed soil that we just manually entered and this red line here, which represents the class 1 riprap. So to do that, I'll click on add granular filter. Okay, so it added a filter layer right here. I can give it a name if I want, but I'll just leave it as is. And then click on this define gradation curve data. This is the gradation of the filter material, which we're going to design right now. Now, like I mentioned in the beginning of the exercise, there's a lot of flexibility as to what sort of design you can make. I think one of the better designs would just be to minimize the number of layers. So let's try to design a layer so that we don't have to come back and create a second filter layer. That would minimize costs most likely and also headaches for the designer. So the design that I've come up with is as follows. I'm going to say the grain size is 10 millimeters, 35, 55, and 85. And that is for the same percent finer we've been using already, 15, 50, 85, and 100. Okay. So if I click OK and then click on plot all gradation curves, we can now see this blue line is the filter gradation that I just added. And as you can see, it more or less is splitting the difference between the red line representing the riprap class 1 and then this brown line, which is our soil gradation. So let's go ahead and see if that is sufficient. Also, I'm going to make up the hydraulic conductivity is 0.2 inches per second. So with the green text right here, we're saying filter D50 is suitable and filter conductivity is suitable. What that means is the layer beneath it, the soil layer, doesn't need a layer between the filter and the soil. Now, if I click on the riprap layer, it says the filter D50 is not suitable. However, I need to change this fine soil type. The layer just beneath the riprap needs to be switched to my granular filter 1. And boom, it looks like the granular filter 1 is satisfactory. So if you click through each of the layers, as long as you don't have any red text to say that the filter D50 is not suitable, you have all green messages that say the layer is suitable, then you're good to go. Okay. So that's it for this exercise where we dealt with the Pier riprap. Specifically, we used this geotextile granular filter design to stabilize the soil material that is beneath the riprap using this granular filter.